Hi, in this video, I'm looking at scalar multiples of vectors. That is where we've got a vector, which remember has a magnitude and a direction, and we're going to multiply them by a scalar, which has just magnitude. So if we do have a vector, such as this vector here, which we might call vector v, it's got the magnitude of whatever the magnitude of v is. This long could be about an inch, 2 centimeters, okay? And it's pointing in that direction, sort of up left, so about 135 degrees maybe, as a guess. And we want to know what happens if I say I want to find what is 5 times v. What would that look like? Well, if I've got something that's just magnitude, it shouldn't be able to change the direction. So 5v would be in the same direction as v, but 5 times longer. So it would be all the way pointing up there somewhere. 1, 2, 3, 4, 5 times longer. So this would be the 5 times the magnitude of v, the length of it, to give us that vector there. But that's if we have it drawn down. If we have a vector that's drawn, we just got to draw it 5 times longer. Or perhaps if I want to know what is half of v, so I want to have 0.5 or half of v, well, that would be something that's in the same direction as v, but only half as long. So that would be the vector that is half the length of v. So whatever I multiply it by, my length just changes by. So if I have a look at a polar form vector, so let's have a look at a polar form vector. So let's say I have the vector w, which is 345 degrees. So if I draw that, that would be the vector that is at 45 degrees to the x-axis. And if I draw a nicer x-axis than that, we'll get a nice 45 degrees. And it is 3 units long. So that would be vector w. And if I want to find out what is 10 times vector w, well, then I'm just multiplying the magnitude, aren't I? I'm just making the magnitude bigger by whatever my scalar is. So that would mean I have 3 times 10 at 45 degrees. And if I was to draw that, it would be very long, probably going off the edge there, somewhere over there, and being a grand total of 30 long, because that's what 3 times 10 is. So we would have the vector 30, 45 degrees. So if we have a drawn vector, we just change its magnitude. If we have a polar form vector, we just change its magnitude. But what about if I've got a Cartesian form? If I've got a Cartesian form vector, so if we're looking at Cartesian form, then I don't have magnitude in my information. So let's have a look at the vector u, and let's have a look at the classic 3-4 vector. So the classic 3-4 vector is going to be easy to work with because its magnitude is 5. So I can draw it as being 3 units across, 4 units up, and 5 units in magnitude. So that's the vector u, and I've drawn it as a v. So I want to know what happens if I do try and change its magnitude. So let's have a look at its angle. We can plug that into a calculator using inverse tan or arctan, and we can get the angle of 53.13 going on degrees. And so if I apply our concept, basically I'll just turn it into polar form now. I know its magnitude and I know its angle. So that means that I have something that's going to be longer. So let's try and work out what will be 5 times the vector u. So that will be a magnitude of 25. at an angle of 53.13 continuing degrees. And I want to know what changes. How long do these sides become? Well, I can have a look at some trig to help me. So this would be 25 cos 53.13 degrees, and this would be 25 sine 53.13 degrees. And if I work out what is 25 cos 53, then I will get 15. And if I work out 25 sine 53.13, and I will get 20. If we use perfect numbers. If I use my rounded answer, then I won't. I'll get close. But if we use the perfect number, whatever it comes out to be, 53.13 then that's what we end up with. And if I go back to my sides here, this side here is 3, and this side here is 15, which is 3 lots of 5. And remember, I was trying to find 5 times u. And here we've got 4 and 20, which is 4 times 5. So my sides have also just been multiplied by my scalar. So our Cartesian form is easy to work out as well, because 5 times a vector is, or a scalar times a vector, is 5 times each of those components. So I have 15, 20. So that makes it nice and easy. If I have polar form, I multiply the magnitude. If I have Cartesian or component form, I multiply each component. And if I have it drawn, it just increases or decreases the length of the arrow. One thing we haven't looked at is what happens if I've got a negative scalar. So what happens, let's go back to our vector w here, which was 345. So what happens, so we've got w equals 345. What happens if I want to find what's negative 2 times w? Well, we've looked, that means I want to do negative 2 times its magnitude, and that's going to give us negative 645 degrees. But a magnitude with a negative value is kind of problematic. We don't like that. So let's have a look at it on a Cartesian plane, on the diagram. So if we have a Cartesian plane, our original w is magnitude of 3 at an angle of 45 degrees. And now I've got, at an angle of 45 degrees, going in the negative direction, 6. That's what it means. So at an angle of 45 degrees, going in a negative direction, we're going to have 6. So a magnitude of negative 6 is really a magnitude of positive 6 in the opposite direction, which means that I need to figure out what is my translation, which is an extra 180 degrees, because I've just translated 180, to work out my overall angle, which in this case would be 225 degrees. So if I've got a polar vector and I'm multiplying by a negative scalar, my magnitude ends up negative, which means I need to make it positive by adjusting the angle. But what about in Cartesian form? In Cartesian form, if I go back to my vector u, which was 3, 4, and I want to find negative 2 times u, well, negative 2 times 3 and negative 2 times 4 gives us negative 6, negative 8. And that's perfectly fine for a Cartesian, because 3, 4 would be, say, there, and negative 6, negative 8 would, say, be somewhere down there, and we wouldn't worry because it's Cartesian, it's just a coordinate. We can simply draw it. We don't have to do any adjustments. So, wrapping up, scalar multiples of vectors. If you're going to multiply a scalar by a vector, all that happens is the magnitude changes by the value of the scalar. So if it's a graphical vector, it's drawn, we just draw it again in the same direction, but shorter or longer by whatever the scalar is. If it's in polar form, then we just multiply the scalar, or the magnitude by the scalar, keep the angle the same, unless we have a negative scalar, which gives us negative magnitude, which is problematic. So we have a positive magnitude with adjusted angle because we can't have a negative magnitude. If we have it in Cartesian form, we can just simply multiply each component by the scalar, and if it's negative, it still doesn't matter. We can just multiply each component by the scalar.